Data centers play a central role in digital transformation, particularly in the field of artificial intelligence. However, their energy consumption is enormous. In Germany alone, it amounted to 20 billion kilowatt hours in 2024. At the same time, energy costs are rising and requirements for climate neutrality are increasing. These factors pose a major challenge for the sustainable and economical operation of data centers. EAVE, Energy Analytics for the Cost-Efficient and Sustainable Operation of Data Centers, offers a solution to this. By using AI-based analyses, the system specifically optimizes energy efficiency and cost-effectiveness in the inference of AI applications in data centers. The system measures and forecasts energy consumption, CO2 emissions, and operating costs of different AI model configurations, including hardware options. At the same time, it analyzes which factors significantly influence consumption and costs. With the help of AI compression techniques such as knowledge distillation, quantization, and NAS, EAVE optimizes the ratio between AI performance and operating costs. This enables decision makers to manage data center operations in a data-driven and efficient way, while also meeting ecological goals. EAVE provides decision support to harmonize AI performance, sustainability, and cost-effectiveness. We now present the EAVE prototype in detail. EAVE is currently available as an open web app and can be accessed via any standard browser. In the Measure tab, a configuration is first specified. That is, the size of the data center, the task of the AI model itself, processors and accelerators, time and place of execution, as well as the number of nodes, accelerators, and cooling load. In the present case, for example, the task of image classification is selected, specifically in the context of steel scrap sorting. Based on this, the Energy Analytics summary shows the costs, energy consumption, PUE value, CO2 equivalents, and emissions for the chosen model in the respective configuration. As a reference, the execution of the model over 3 months is used. The main energy source of the country of execution is also listed. This is followed by a detailed overview of the composition and calculation of the individual aspects. In the cost overview, the costs for running the model over 3 months are given based on the configuration, along with their calculation. In addition, information on the total energy consumption of data centers and energy price developments in the selected country is provided. The energy consumption over 3 months, its calculation, and a comparison with the energy consumption of a 4-person household are visualized in the next section. The PUE value is indicated based on the chosen configuration. It shows how energy efficiently the data center operates. The graphic also displays the average PUE value in Germany, as well as regulatory thresholds that must be met from 2027, respectively, 2030 onward. For the chosen configuration, CO2 equivalents and emissions are also displayed based on the energy mix of the respective country. Finally, the table shows factors that significantly influence the energy consumption of data centers as well as their operating costs. A causal analysis was carried out for this purpose. The Predict tab forecasts, using an AI model, specifically a Bayesian neural network, in which country and at what time the execution of the chosen configuration would be optimal, that is, most energy and cost efficient. Among other things, historical energy price developments are used to forecast future energy prices. Subsequently, the costs, energy consumption, PUE value, and CO2 emissions of the originally chosen country and time period are compared with the values of the forecasted optimal time and location. In the Optimize tab, EAVE focuses more strongly on the efficiency of AI models. In the present case, image classification in the context of steel scrap sorting with a PREACT ResNet has been selected. The Optimize tab shows the costs of running the model, its accuracy, energy consumption, size, and CO2 emissions. AI compression methods can then be selected with the goal of shrinking an originally very large AI model while maintaining performance similar to the original. The method of neural architecture search already shows a strong reduction in model parameters, over 80%, as well as almost 40% cost reduction. Alternative models, such as a vision transformer, can also be selected. Methods such as knowledge distillation and quantization result in a slight reduction in model accuracy, but also in savings in costs and energy of up to more than 80%. The trade-off analysis shows Pareto optimal models that serve as a basis for decision-making. The information helps to assess how expensive, fast, accurate, and large a model is. If the goal is to select a particularly small model with low costs, high energy efficiency, and accuracy, for example, for model execution on mobile devices, the Vision Transformer model compressed through knowledge distillation would be the best choice. Further information about EAVE can be found on our website or contact us directly. We welcome your participation in the evaluation of EAVE.